This is a recording of a journal article published by Nature in 1923. Expansion of the wings of Lepidoptera after emergence from the chrysalis. No one who has watched a butterfly or moth emerging from the chrysalis can fail to have been impressed by the rapid expansion of the wings. This expansion is not real growth, but merely the opening out of the contents of a carefully packed parcel, and the general character of the changes which occur in the process is well known. The true growth of the wings takes place and is completed in membranous sacs just within the walls of the chrysalis, and the form of the wings can be distinguished from the outside. The position of the wings during their development is such that the upper surface of the forewing is next to the wall of the chrysalis, and within a day or two from the time of hatching, the colors and markings can in many cases be recognized. Each wing consists of two separate membranes, united with the nervures on which the scales are mounted, the stems of the scales entering sockets in the membranes placed in fairly symmetrical rows, though the irregular shape of the spaces between the nervures prevents the symmetry being exact. The point to which the present note is intended to direct attention is the numerical relation between the size of the pupil and expanded wings, and the reason for the constancy of this relation. In all the Lepidopterous wings which I have examined, the pupil wing has very nearly 1/3 of the dimensions of the wing of the perfect insect. If the fully developed wing is removed from the chrysalis and sectioned, the reason for the 1:3 ratio is immediately evident so far as regards extension parallel to the nervures, but the accordion folding whereby the scale-bearing membranes expand in a direction at right angles to the nervures is rather more complex. The second parallel to the nervures is shown in Figure 2 and diagrammatically in Figure 6. Here, the wing membrane is seen folded so that the distance from fold to fold is the same as the depth of the fold, and therefore the extended is 3 times that of the folded dimension. To realize the character of folding in the other principal direction, imagine a series of camera bellows fully extended. A1, A2, etc. to be placed side by side, so that the sides C1, C2, C2, C3, etc. will remain in contact when the bellows are contracted. Then remove the lower sides B1, B2, etc. and join the free edges of C1, C2, C2, C3, etc. It is clear that the surface thus formed is developable, and that if, to start with, the bellows are compressed to 1/3 of their extended length, the developed surface will in all directions have 3 times the dimension which it has when folded. The section of the membrane cut in this direction presents a much more complex appearance than that parallel to nervures. The compression to 1/3 of the extended dimension in the transverse direction appears to be due to the space occupied by the accordion folds, and a diagrammatic sketch of the folded membrane seen in plan with the scales removed is given in Figure 8. The positions in which the sockets for holding the stems of the scales occur are shown at D in Figures 6, 7, and 8. In the pupil wing, the scales are closely packed like the pile of a carpet, but after expansion lie close and nearly parallel to the extended wing membrane. See Figures 4 and 5. The mechanical means whereby the extension is effected is, I believe, of much the same nature as pumping up a pneumatic tire, fluid being injected into the nervures by the muscular action of the body, but this is a point requiring further observation. So far as I know, it is only in the Lepidoptera that the 3-to-1 expansion occurs, but it seems probable that the same form of stiffening by injection acts in all wings supplied with nervures.